Hello everyone, and happy International Day of Light from the student chapter here at the Medical University of Vienna and its Center for Medical Physics and Biomedical Engineering. So today is the International Day of Light, and maybe you're aware what it means, but in case you're not, today is the birthday of the first laser. He's 60 years old, and he's been pulling a lot of weight in many different domains. And so we wanted to celebrate this occasion by building a laser together with you. But why would you build a laser in the first place? To that, I feel there are many good answers. Lasers are very useful in many different contexts. For instance, in telecommunications, they are used to send information through optical fibers. In metrology, they are used as a way to calibrate other instruments. And in the context that matters to us here at the Medical University of Vienna, lasers are very useful, both for medical purposes and also for research. This is, however, only the tip of the iceberg, and lasers are in fact used in many more aspects of daily life. It is safe to say that, right now, unless you're on a desert island, you are surrounded by everyday objects that either use lasers to operate or have been built using lasers at some point. The other answer to this question, and I would say the most important to me, is that lasers are very cool. And that's why they've been a part of sci-fi imagery since forever. But what is a laser? It is a little known fact that laser is actually an acronym for light amplification by stimulated emission of radiation. And I think it explains it pretty well. We amplify the light by stimulating the emission. Without going into too much details, because quantum mechanics is very scary, when light and matter interact on a fundamental level, a few things can happen. I think the most straightforward possible interaction is simply absorption. Light hits a piece of matter and its energy is transferred to the matter. Think, for instance, of a black rock left in the sun. It gets hot. The second possible interaction is spontaneous emission. Energy is released by matter in the form of some random light. This naturally happens when matter has received energy in some way and gets rid of it by emitting light. You can think of fluorescent light bulbs, for instance. These two pathways are the most straightforward. But quantum mechanics isn't always straightforward. This guy postulated that for symmetry reasons, a third pathway has to exist. It is called stimulated emission, when light interacts with matter that is already full of energy. It can force it to somehow emit a copy of itself. If you think of light as being made of packets of energy called photons, when one of these photons hits a piece of matter that is already full of energy, it can stimulate the emission of a clone of itself. And this is the mechanism that lasers use. All the packets of light emitted by a laser are all the same, in terms of colors, of polarization, energy, anything you can think of. And when we say the same, it also means that they have the same momentum vector, which means they all go in the same direction. This in turn explains why lasers propagate in these distinctive beams of light, unlike the light of a light bulb. Now that we know what they are, we have an idea of how to build one. We need energetic matter that is ready to emit a bunch of photons. And we need a way to select which photons are going to clone themselves or reproduce by stimulated emission. And so because of this, pretty much all lasers are made of three main components. First is something we call a gain medium. This is a carefully selected piece of matter. There are many different kinds: atoms, molecules, semiconductor junctions, XMS, etc. And pretty much in any forms you can think of. Some are gases, some are liquids, some are solids. In principle, you choose the gain medium for what kind of color it can emit. In our case, we choose a specific crystal. It is called a sapphire-doped titanium crystal. It is a very common choice for a gain medium. It emits in the near infrared around 800 nanometers. We need to pump this medium full of energy. This is done on a case-by-case basis and depends on the medium itself. It can be done electrically, which is typical for gas-discharged lasers, or for instance for diode lasers. It can be done using light, typical for diode-pumped solid-state lasers, or even in pretty exotic ways, if you look at excimer laser, for instance. The goal is to achieve what we call population inversion, which means that at a given time, we want a majority of the gain medium to be in a high energy state and ready to emit light. This is harder than it looks because matter doesn't like staying at high energy states for long. In our case, we're going to use the light of another laser to pump our Titanium-Sapphire crystal full of energy and ready to emit. The third component is a way to select what light is amplified. And this is done using something that we call a cavity. The simplest cavity is just a pair of mirrors turned toward each other. When there is light inside the cavity, if its angle of propagation is not perpendicular to the mirrors, it will just bounce off and go away. But light emitted horizontally will bounce from one mirror to the other forever, just like in these elevators with two mirrors, and you see infinite reflections of yourself. The other important effect is that because of the wave nature of light, you will observe destructive interference if the wavelength of the light emitted doesn't somehow match the size of the cavity itself. Of course, in general, you want some output, so one of the two mirrors is less than perfectly reflective, so some of the light can come out.
Great. Thank you very much, Gabriel, for these nice explanations. So now that we know what lasers are and how they work, we have an idea of how to build one. But wait, the details can get a little tricky. So at this point, we would like to thank Angelika Unterhuber, who is an expert on laser science at our center. Without her knowledge, this video would not have been possible. And as a side note, in case you find all the necessary components for building a laser in your garage, with a twinkle in the eye we would like to advise you, do not attempt the following build at home if you don't want to burn yourself or permanently lose your vision. As you learned before, at the heart of a laser we need a gain medium. In principle, you would choose the gain medium as a function of the application, the wavelength or the color of light that you need. Today we are building a Titanium-Sapphire laser. So what we choose is a sapphire-doped titanium crystal as a gain medium. This is how such a crystal looks like. As you can see, it is very compact, in this case about 2 by 2 by 4 millimeters. A massive feature of the Titanium-Sapphire laser is that it not only can emit light continuously, but also can produce ultra-short pulses of light with very high peak powers. These ultra-short pulses are key to numerous fields of science and technology and are an extremely valuable tool, for example, in the investigation of ultra-fast chemical reactions, in biomedical imaging, for example, multiphoton microscopy, where you can investigate on cellular metabolism, but also in industrial applications such as material processing. Here you can see a close-up of how the crystal is mounted. As you can imagine, when operating the laser, the crystal gets very hot while we permanently focus a pump laser on it. So what we need is a good cooling system. And you can see that we wrapped the crystal in indium foil to better dissipate the heat. In the following, we want to show you optical components we need for building our cavity. When you wake up in the morning and go to the bathroom, you may use a mirror which essentially reflects back the light from your tired face into your eyes, giving you the information, man, I need to shower. In a similar way, we use mirrors to reflect the light in any direction that we want. Some of those mirrors have surfaces with very useful properties. For example, they may reflect some colors, while other colors are transmitted. A surface can also be changed in a way that light of a specific wavelength or color is reflected with very little losses. To guide the laser beam, we need to position the mirrors exactly as we want them to be. For that we can use kinematic mounts. We can put the mirror into the kinematic mount and then tilt it in any direction using 3 screws, which we call set screws. The mount can be attached to the optical table. As you may have experienced in your own home, it can't harm to clean from time to time and get rid of a little dust. In our project, it is essential to clean all the optical components to guarantee optimal performance. Even a little dust can impact the performance and the stability of the laser. To make this a little more practical, we will watch Gabriel while mounting a mirror in our cavity. Later on we will give you more insight in how we optimize the positioning of the individual mirrors. It is important to attach the kinematic mount firmly on the optical table to make sure it doesn't move at a later point. As I said before, essentially what we want the mirrors to do is to guide both the light of the pump laser and the laser that we are building. Further, we need a lens for focusing the pump beam on the crystal. You might have already used a magnifying glass in the sun to burn paper by focusing all the energy in a small area. The way we use the lens is very similar to this. Finally, at one end of our cavity we need an output coupler. It acts in a similar way as a mirror, with a small difference. In our case, 99% of the light on the output coupler is reflected back into the cavity, but 1% can pass through the output coupler. And this 1% finally is the output of our laser. So let's get started with the build. Here we mount the crystal on the optical table. We can later on fine adjust the position of the crystal to make sure it is exactly in the focus of the pump beam. To accurately guide the beam of our pump laser towards the crystal, we make sure that it passes through two small holes, which we call pinholes, and we can use the mirrors to adjust the beam. In the dust particles you can see how the beam is reflected by the mirror into the first pinhole. In this close-up you can already see the green pump laser being focused on the crystal. Pay attention to the orange light. This is fluorescence emitted by the crystal. Later on we will align the cavity to use the concept of stimulated emission in order to produce lasing. Let us walk through the system that we have so far. We are now following the beam of the pump laser, which we are using to energize the crystal to achieve population inversion. After the pinholes, the beam is focused on the crystal. In this setup, we then use multiple mirrors to reflect the beam back and forth within the cavity. Finally, you can see a red spot after the output coupler. So far, this is only the fluorescence of the crystal without any gain through lasing, as the cavity is not aligned yet. At this point we would like to take a short break and show you the effect of a laser goggle. This is important safety equipment when working with lasers. For example, this exemplar can stop the green light beam from hitting our eyes, but we can still see the red fluorescence. We will illustrate this by putting the laser goggle in front of the camera, and as you can see, the green light vanishes, but we can still see the red fluorescence from the crystal. By now, the cavity is set up with all mirrors and the output coupler in place, and we now need some mechanical alignment to reflect the beam back and forth the way we want it to. Using the set screws on the kinematic mount, Gabriel is overlapping both the beam and its reflection from the opposite mirror. The height of the beam can be checked using a specific tool with holes in it and then be adjusted if necessary. We can now lean back a little bit and watch Gabriel work. The alignment is a process that can take multiple hours. But don't worry, we're going to let Gabriel and Angelica work. Turn off the camera and in the meantime grab a cup of coffee. Yaddy, the system is now in a state where we already get some lasing. So you can see that we put a measurement probe at the output of the laser, which allows us to measure the power of the emitted laser beam. Using this we can further optimize the cavity alignment and try to increase the power at the output. At this point we are lasing at about 42 milliwatts, but I'm pretty sure Gabriel can give us some more. In the meantime we will illustrate the point where we get lasing by starting with weak intensities of the pump laser, and then we will gradually increase the power. What we see in the beginning is only the red fluorescence of the crystal. When increasing the intensity of the pump laser, at one point the output of our laser becomes more intense, and we know that the system has started lasing. Our system is now lasing at about 51 milliwatts. As only 1% of the power is coupled out, this implies that about 5 watts of optical power are circulating through the cavity, so you really don't want to put your hand in there. So far, we are only lasing in continuous mode, which means that the laser continuously emits light. Through a technique called mode locking, we can bring the laser to emit light in short pulses. As mentioned in the beginning, the high peak power in these pulses is very useful for many applications. For many applications it is very useful to couple the output of the laser into optical fibers. Hannes will talk about one of these applications later on. One important feature of a Titanium-Sapphire laser is that you can change the wavelength that the laser emits in a very broad range. We measure the output of a laser with a spectrometer, and you can see Gabriel changing the emission wavelength from about 870 nanometers to 770 nanometers. So now you know how a Titanium-Sapphire laser is built. Let's stop the technical part now and switch to Hannes. He will give you insight into his research where he is using a Titanium-Sapphire laser.
Okay, so here's what we call an optical coherence tomography system. It uses the light of a Titanium-Sapphire laser, just like the one you just built, to image biological tissue. With this device here in particular, we're studying the front part of the eye. Since the light not only reflects, but also penetrates to a certain degree, we can actually acquire images from within the tissue. This, as you can imagine, is very helpful for research purposes, but medical doctors can also use it to monitor or diagnose different ocular diseases like cataract, for instance. Just like before, safety is very important when working with lasers. So this system is designed in a way that only a very small fraction of the power of the laser actually reaches the eye. But how about I show you? So here we can very nicely see the lens. And if we move back a little bit, we can see the cornea. And 3, 2, 1. And that's it already.
If we now take a look at one of the scans, after some post-processing, we can visualize the morphology of the cornea with high resolution, all thanks to some particular properties of the Titanium-Sapphire laser. As you could see before, if we scan a little deeper, we can also acquire images of the lens and iris, for example. And this brings us to the end of our little video about the Titanium-Sapphire laser. Thanks for watching. If you enjoyed this video, come check out our LinkedIn page in the description and see what else we're up to. We would like to thank Angelika Unterhuber, René Werkmeister and all the other amazing people at our research center at the Medical University of Vienna for supporting us in the making of this video. Mark your calendars for the next International Day of Light. And don't forget, lasers are awesome!